Welcome to Calculus 2. I'm Dr. Jeff Grove. We're going to begin with a review of the end of Calculus 1. I'd like to first recall to your memory the definition of the Riemann integral. The idea was to find the area of the undergraph of a function between A and B. And we did this by making a partition, perhaps of unequal width, with little partition points x1, x2, and so on. Then, the integral from A to B of f of x dx was equal to, we would make little refinements of these partitions, have a sequence of partitions, so that the maximum subinterval width tends to 0. We'll take the limit, and in this case, let's call the maximum subinterval width the norm of the nth partition. We want that maximum subinterval width to go to 0, and then we estimate the area of the undergraph by adding up areas of rectangles. That's the sum as k goes from 1 to n. We use sampling points ck, and we have little delta xk. So on each little subinterval, we'll have little sampling points. And then multiplied by the interval width. Height times width gives you the area of a rectangle. Add them up and take the limit as the maximum subinterval width goes to 0 as we get finer and finer partitions. That gives us the exact area of the undergraph, and that is called the Riemann integral. I want to recall to your memory something called the extreme value theorem. The extreme value theorem says that a continuous function defined on a closed and bounded interval attains both its absolute maximum and its absolute minimum on that interval. It is necessary that the interval be closed. If you're dealing with an open interval, let's say from here to here, the function may attain neither the minimum or maximum on that interval, because the minimum, absolute minimum, occurs outside of the interval. Here, that's not in the interval that we're working on. The absolute maximum may occur outside of the interval. So the closedness of the interval is necessary. It's also necessary for the interval to be bounded. It can go off to infinity, in which case you may never achieve the absolute minimum. It is also necessary for the function to be continuous. If it's not continuous, it may not achieve an absolute minimum or an absolute maximum. Consider a function that does this. Suppose it has a little break. The function is defined on a closed and bounded interval. It doesn't achieve an absolute maximum or an absolute minimum, and that's because the function fails to be continuous. You should know that we did not prove the extreme value theorem in Calculus 1. We merely stated it. We waited until an upper division course in real analysis to prove this theorem. Analysis is the study of limits and their applications. Real analysis deals with real-valued functions of real variables, limits, and applications. Complex analysis deals with limits and applications for complex-valued functions of complex variables. There are different forms of analysis besides those two, but those are two main branches. You should also remember how to calculate the average height of a function. The average between a and b, thus some function f, is 1 over b minus a, the integral from a to b, f of x dx. One way to see that is as follows. The average is approximately the sum as k goes from 1 to n of f of xk divided by n, where here we're assuming that we've divided some interval a to b into a partition. We're adding up the height of the function at various points, sampled at, say, the partition points xk, and dividing by how many we've added. That's not going to give you the exact average. To get the average, you need to take the limit as the number of partition points tends to infinity. In other words, the average should equal the limit as n goes to infinity, sum as k goes from 1 to n of f of xk divided by n. This looks similar to a Riemann sum, but not exactly. You need to know that the width of each subinterval, and here we're assuming that the subintervals are of equal width, is the length of the interval divided by how many times you're slicing it up into n pieces. This gives us then the limit as n goes to infinity. We're going to write this as the sum as k goes from 1 to n of f of xk. Instead of writing 1 over n, let's write b minus a over n. To compensate, we can write 1 over b minus a. Taking the limit, what we have here on the end is delta x. We'll have 1 over b minus a times the integral from a to b of f of x dx, demonstrating this does indeed give you the average height of the function. As a matter of fact, we make this a definition. The average height of the function is this. We're now going to review the three major theorems from the end of Calculus 1. The first is the mean value theorem for definite integrals. This is not the mean value theorem. This is the mean value theorem for definite integrals. And sometimes I say facetiously, the cruel value theorem. We'll abbreviate this as MVTDI. It says that a continuous function on a closed and bounded interval attains its average. Let me state this in another way. Another way of stating the theorem is, if f is continuous on a closed and bounded interval ab, then there exists some point c between a and b such that the height at C is equal to the average height. To prove this theorem, note that by the extreme value theorem, there exists a little m and a big M, such that for all points x in the interval AB, little m is less than or equal to f of x is less than or equal to big M. There are places within the interval where the function achieves its absolute minimum and its absolute maximum. Everywhere else, the function value is in between those two values. If we integrate all three parts, when we integrate a constant m, function of constant height m, from A to B, we get the area of the rectangle, which is height times width. This will be less than or equal to the integral from A to B of f of x dx, and that's less than or equal to the integral on the right-hand side, which is big M times b minus a. Dividing each part of the inequality by b minus a, which is non-negative, we obtain m is less than or equal to 1 over b minus a integral from a to b f of x dx, and that's less than or equal to big M. In other words, the average height of the function is intermediate to the absolute minimum and the absolute maximum. Go figure. By the intermediate value theorem, there has to be some place in between. By the way, backwards capital E means there exists. And upside down capital A means for all. These are the two logical quantifiers. There exists C in AB such that the height at C is the intermediate value. And that's the end of the proof. We're now going to state the first fundamental theorem of calculus. Well, in some texts, it's the second fundamental theorem of calculus. As you'll see, the first and second fundamental theorems of calculus are logically equivalent. So which one you call first and which one you call second is kind of irrelevant. Maybe we should just call them both the fundamental theorems of calculus. Nonetheless, we'll call this the first fundamental theorem of calculus, or FTC1. The first fundamental theorem goes like this. If f is continuous on a closed and bounded interval AB, then this function, which I'm going to denote by capital F of x, which is going to be the integral from a to x, f of t dt, this function is an area function. We're finding the area of the undergraph from a to x. We're only assuming that the function f, little f, is continuous, but the function big F is differentiable. In other words, the averaging process of the integral smooths this out, and you obtain from a continuous function one function that is one level higher in smoothness. It is differentiable. But not only is it differentiable, we can tell you what its derivative is. The derivative is f of x. Think about this. We have an area function. when we calculate the slope function of the area function, we end up with the original function. Think about what that means. That means slope finding and area finding are like opposite processes. When you area find and then you take the derivative, you end up where you started. They undo each other like multiplication and division, like addition and subtraction, like a function and its inverse. These are inverse processes, slope finding and area finding. This is astonishing. We definitely have to see the proof of this because it seems like there's no way. But there it is. In a way, you can see that since integration is limits of sums, it involves sums, and differentiation involves limits of differences, maybe it shouldn't be too surprising that area finding and slope finding are opposite processes. Let's go through the proof. We're going to look at the derivative of the integral from a to x, f of t dt. We need to use the definition of the derivative here. Remember, that's the limit as h goes to 0 of, we evaluate the function at x plus h and then subtract the evaluation at x and divide by how far in between, h. Now, the first term in the numerator gives us the area from a to x plus h, and we're subtracting the area from a to x. What's left over should be the area from x to x plus h. And I'll put this 1 over h out front. You might now see that what we have here, b minus a, is h. We have out front 1 over b minus a. This is an average. We can apply the mean value theorem for definite integrals to assert that we get the limit as h goes to 0 of f of c, where c is someplace in between x and x plus h. So c is trapped. It's trapped between x and x plus h, but h is getting smaller, so we have walls that are closing in. And c is in between, and as the walls close in, c gets squished to x. And that's the end of the proof. So we've now established once and for all that slope finding and area finding are inverse processes to each other. We're going to continue that in the second fundamental theorem of calculus. We'll call this FTC2. It goes like this. If f is continuous from the closed and bounded interval AB, and big F is any antiderivative of little f. Remember, every function that has an antiderivative has infinitely many of them, but they differ by no more than a constant. Then the integral from a to b of little f of x dx is equal to big F of b, the upper limit, minus big F of a, evaluated at the lower limit. This will be an amazing theorem because it says in order to calculate definite integrals, we don't need to calculate limits of Riemann sums that the definition would require. Instead, All we have to do is find any antiderivative at all, evaluate at the endpoints, and subtract. This theorem will make us very happy. So happy, it's kind of a blissful face. After all, what are theorems for but to help make things easier for you? And this theorem definitely makes things a lot easier for you. To prove this, we'll let g of x be the integral from a to x, f of t dt. By the first fundamental theorem of calculus, big G is an antiderivative of little f. That means big F and big G differ by no more than a constant. Then let's consider g of b minus g of a. That will in fact be f of b minus f of a. But it's also the integral from a to b, f of t dt, minus the integral from a to a, f of t dt. But the integral from a to a, the area under a single point, is 0. And so the proof is over. Let's prove that FTC2 implies FTC1. That will complete our proof of the equivalence of these two. We just used the first fundamental theorem of calculus to prove the second fundamental theorem of calculus. Let's see if we can use the second fundamental theorem of calculus to prove the first fundamental theorem of calculus, and so they'll imply each other. They'll be logically equivalent. Let's look at the derivative of the integral from a to x, f of t dt, in light of the second fundamental theorem. That's the derivative of big F of x minus big F of a, where big F is an antiderivative of little f. Remember, antiderivatives are by definition functions that satisfy big F prime equals little f. When we take the derivative of big F evaluated at x, we get little f. When we take the derivative of big F evaluated at a, we get 0, because the derivative of a constant is 0. And that shows that the second fundamental theorem of calculus implies the first. Now you know why the two fundamental theorems of calculus are sometimes enumerated differently in different textbooks or by different professors. They are logically equivalent, so it really doesn't matter which one you call first and which one you call second. It really depends upon the inclination of the professor as to which he or she likes to prove first. I'd like to review the integration method called substitution, which I'll just refer to as U-substitution. It's based upon reversing the chain rule. So I want to recall the chain rule. The chain rule says that if you take the derivative of a composition f of g of x, you take the derivative of the outside and leave the inside alone, and then multiply by the derivative of the inside. So that way, if we're integrating f prime of g of x times g prime of x dx, when you integrate a derivative, they undo each other, and you just end up with f of g of x plus an arbitrary constant. Remember, the indefinite integral stands for the class of antiderivatives. The method of substitution then works like this. I'll call this U-substitution. If we start out with f prime of g of x times g prime of x dx, we'll set u equal to the thing that has its derivative lying around. It'll be g of x. That means du, which often we would write as du over dx, but I'm multiplying the dx to the right, will be g prime of x dx. I'll put this in a box because this is a side computation. The integral may now be expressed as f prime of u du. Notice that g prime of x dx goes away to become du, g of x becomes u, and now it's clear when we integrate f prime, we will get f of u plus c, but replacing the u back, because the problem is supposed to be stated in terms of x, we get f of g of x plus c. A formula that's very handy to use, and I definitely want you to know this, is that if I have f prime of x over f of x, that's the log of the absolute value of f of x plus c. We'll prove this using u substitution. We'll set u equal to the thing that has its derivative lying around, so that du is f prime of x dx. You can see then that the integral becomes du over u, and that's clearly the log of the absolute value of u plus c, and substituting back the log of the absolute value of f of x plus c, verifying this formula. So in fact, you don't have to do this work again. Anytime you see f prime over f, you get log absolute value of f of x plus c. Let me give you an example. Suppose I'm integrating 2x over x squared plus 1 dx. The derivative of the denominator is 2x. So I can go straight to the answer, the log of the absolute value of x squared plus 1 plus c. In this case, the absolute values are superfluous because x squared plus 1 is already non-negative. This is very different from the problem, the integral of x squared plus 1 dx, which we spent some time in Calculus 1 proving is the arctan of x plus c. This is the one. This is the one you're going to remember. In fact, you're going to memorize it right now, and you're going to make a clear distinction between these two cases. Let me give you another example. If I have x over x squared plus 1, it's not quite what I want. I want the numerator to be 2x. But there's an old Spanish proverb. Take what you want, then pay for it. I get what I want. I just have to pay for it, with the 1/2 out front. So the answer is 1/2 log absolute value of x squared plus 1 plus c. Let's suppose I have the integral of 1 over x minus 1 squared plus 1 dx. This may not look like the 1, but it really is. Suppose I set u equal to x minus 1, so that du is dx. Then the integral is transformed into 1 over u squared plus 1 du. That's the arctangent of u plus c, or the arctangent of x minus 1 plus c. Let me give you an example. How do I integrate secant of x dx? This is one you're going to remember, but we're going to use the f prime over f method to calculate the antiderivatives. Here's the idea. And this is a sort of garbage can calculation. It seems the only way to explain what comes next is that some professor was pacing in his office one day wondering, how do I do this? And happened to be passing his garbage can, and there it was. Exactly what was required. it was secant x plus tangent x over secant x plus tangent x. Now, why does that help? First of all, it's okay because I'm multiplying by something that's equivalent to 1. So I'm not changing the value of the expression. I'm only changing its form. It helps because when I distribute and reverse the order of the subtraction, I'll write this as secant x tangent x plus secant squared x over secant x plus tangent x dx. Don't be abusing my dx. If you start abusing that differential, it will abuse you back. So be careful and don't abuse the notation. Don't leave it off. Don't throw it around. Always take good care and know exactly what's going on with that dx. Now, notice that the derivative of secant is secant tangent. And the derivative of tangent is secant squared. I'm in the form f prime over f. The answer is the log of the absolute value of secant x plus tangent x plus c. You'll probably want to just remember that the integral of secant x dx is log absolute value of secant x plus tangent x plus c. Though this is an interesting method to remember. You can apply it to the integral of cosecant x. You should try it. There are certain integrals that you should know based on geometry. For example, if I'm integrating from 0 to 2 pi sine of x dx, you should know that sine completes one period in 2 pi units, and you will have a positive bump and a negative bump. So you obviously get 0. If you integrate from 0 to pi cosine x dx, thinking about the geometry of cosine, it completes one cycle in 2 pi and half a cycle by the time you get to pi. You'll have half a positive bump and half a negative bump. So when you integrate cosine over half a period, you still get nothing. I want you to memorize certain values of integrals. Here, I'm integrating sine, but only to pi over 2. I'm getting half a bump. What is the area under 1/2 of a bump on the sine curve? It's pretty easy to figure out. We can easily find the antiderivative, minus cosine x. This will be minus the cosine at pi over 2, minus the cosine at 0, being very careful with the parentheses. The cosine of pi over 2 is 0. The cosine of 0 is 1. So the answer is positive 1. In other words, half a bump gives you 1. So I ask you, what's the integral from 0 to pi of sine x dx? What's the area under 1 bump? 1 bump gives you 2. So I want you to remember the following phrases. Half a bump gives you 1. 1 bump gives you 2. Consider the integral from negative 2 to 2 of the square root of 4 minus x squared dx. What is the value of this definite integral? We will have methods for applying the fundamental theorem of calculus to this later in the course, but there's a much easier way. You should know that if I have y equals the square root of 4 minus x squared, when I square both sides, I'll get y squared is 4 minus x squared. And if I move the x squared over, I'll have x squared plus y squared equals 4. That's a circle of radius 2. But this root is the principal square root. It's not just any square root. It always gives you the non-negative one. So we're not going to get the negative part. When we integrate, we will only get the area of the upper half circle. It's 1/2 the area of the circle. How do you find the area of a circle? The area is pi r squared. Pi r squared. So the answer to this definite integral is 2 pi. I want you to be able to calculate definite integrals geometrically in cases like this. So I want you to know this for the exam. It's time you were introduced to the other one. The other integral that I'm asking you to memorize. If I have the integral of 1 over the square root of 1 minus x squared, I get the arcsine of x plus c. You should also note that when I write a square root, I put a downward flange at the end of it. This is good engineering form. We need to be very careful about how we communicate just exactly where our square roots end. Students often write things so badly, it's really unclear. Even to themselves, from one line to the next, they can forget where that square root terminated. Maybe terminated too quickly or too far, based upon how poorly things are written. To avoid your bridges from falling down, I want you to put the downward flange at the end of your square roots. I have an old calculator, and on that calculator, the square root button symbol has that downward flange. I'm not making this up. This is good form. What is an odd function? Is an odd function a function that does inappropriate things in social settings? No? What is an odd function? I want to give you an example real quick of what we mean by an odd function. Your prototype for odd functions will be x cubed. And I wanted you to see what happens when you replace x by negative x. You get negative x cubed, which is negative x cubed, and that's the negative of the original function. In other words, for odd functions, negatives pull out. We'll make this a definition. A function f is odd if f of negative x equals negative f of x. What this is telling us is, whatever an odd function does at x, it does the opposite at negative x. Think about what you would have if you integrate an odd function from negative a to a. If you integrate from negative a to a, you have to get 0 when f is odd. This is something you need to know. I'll show you an example. Suppose I'm integrating from negative 1 to 1 x times the square root of x squared plus 1 dx. Since this integrand is odd, I know immediately that the value of this integral is 0. You might be wondering, how do I know whether or not this integrand is odd? Well, if f of x is x times the square root of x squared plus 1, then what is f of minus x? Notice that we get a minus x in front, and then minus x squared plus 1 under the radical. The negative under the radical gets squared away. So we get negative x times the square root of x squared plus 1, which gives us the negative of the original function. Well, the negative pulled out. The integrand is odd. Actually, the first factor of the integrand is odd. The second factor of the integrand is even. Even functions satisfy f of negative x equals f of x. Squares, for instance, square negatives away. So we have an odd function times an even function. As far as even and odd functions go, whenever you multiply an odd function times an even function, you get an odd function. One negative will pull out from the first factor and then disappear from the second factor. You get one net negative out of the whole thing. So it's still odd. That's not true for numbers. It's true for functions. What if I'm integrating 1 over 3x minus 1? Note that the derivative of the denominator is 3. I'm missing a 3 on top. I wish it were of the form f prime over f, but it's not. But I get what I want. I'll just have to pay for it. So the answer is 1/3 log absolute value 3x minus 1 plus c. What's the integral of tan x dx? The trick here is, of course, to break tangent into sine over cosine. And then to think, what is the derivative of cosine anyway? Isn't the derivative of cosine minus sine? I need a minus. So I'll put in 2 negatives, and I'll get minus log absolute value cosine x plus c. What if I'm integrating x plus 1 over x squared plus 1 dx? It's kind of in between the 1 and the f prime over f case. We should break this up into x over x squared plus 1 dx plus the integral of 1 over x squared plus 1 dx. On the first term, we need a factor of 2 and an additional factor of 1/2. So the answer is 1/2 log absolute value of x squared plus 1 plus the arctangent of x, all plus c. There are functions that have no elementary antiderivative. In other words, the antiderivative cannot be expressed in terms of a finite number of operations of addition, subtraction, multiplication, division, roots, exponents, exponential functions, logarithms, or trig functions. E to the x squared is such a one. This has no elementary antiderivative, which means evaluating these integrals is kind of impossible for you at the moment. Nonetheless, I could ask you to calculate the limit as h goes to 0, 1 over h, the integral from 2 to 2 plus h, e to the x squared dx. Note that the fundamental theorem of calculus is out of the question, since you can't find an antiderivative for e to the x squared. It has no elementary antiderivative. So we're going to have to rely on other theorems in order to calculate this limit. You know I'm going to give you something like this because I love this sort of thing. I'm going to use the mean value theorem for definite integrals because I have an average here. This is going to be the limit as h goes to 0. I'm not doing anything with the limit yet. I'm just carrying it forward. Make sure that things that you aren't doing anything with get carried forward. A lot of times students fail to write things that they aren't actively working on. This is going to be e to the c squared, where c is between 2 and 2 plus h. C is in that trapped wall, kind of closing wall situation. C is between 2 and 2 plus h, but h is going to 0. So c gets squished to 2. So the answer is e to the power of 4. A lot of integrals are made easier by taking advantage of the fact that the integrand is even. You remember f is even if f of minus x equals f of x. This leaves a certain symmetry property for these integrals. If you're going from negative a to a, because you get the same thing at a as you do at negative a, that means you may as well integrate from 0 to a and double it. So whenever f is even and you're integrating from negative a to a, you can just double the integral from 0 to a. Let me give you an example. Suppose I'm integrating from negative pi over 6 to pi over 6 of the cosine of 2x dx. Because cosine is even, we can just call this twice the integral from 0 to pi over 6 of the cosine of 2x dx. When we calculate an antiderivative of cosine 2x, don't forget to divide by 2. So we'll have 2 divided by 2. We'll end up with sine of 2x, evaluated from 0 to pi over 6. So this gives you the sine of pi over 3, 2 times pi over 6 is pi over 3, minus the sine of 0, the sine of 0 is 0, the sine of pi over 3 is the square root of 3 over 2. This is easier than if we had evaluated from negative pi over 6 to pi over 6. There are several things that I'm going to require of you. I want you to use memory, I want you to form concepts, and I want you to proceduralize those concepts. Let me tell you about a 40-year-old Italian woman who had encephalitis. Encephalitis is an inflammation of the brain. As a consequence, she had permanent brain damage in her lateral temporal lobes. She retained the ability to multiply 3-digit numbers and carry out exponents. She still had mathematical operations down. She just didn't know what any of it meant. Think about how tragic that would be. She was proceduralizing these notions, but she had no idea about the meaning. The conceptual part was gone and impossible for her to recover. That's tragic. We want to form proper concepts in your minds. We also want to proceduralize them. There was another man, his name was E.P., lived in San Diego, and had encephalitis, but his encephalitis damaged his hippocampus. As a consequence, he lost the ability to form new memories. Over the course of 10 years, he met with researchers 200 times at his house, his apartment, and each time the researchers showed up at his door, it was a new introduction. He could not remember who they were. Imagine how tragic that would be. As a matter of fact, the use of memory is very key in the smooth execution of computer programs. You can recalculate things over and over from basic principles, but to do so makes programs run very slowly. It's far more efficient to store intermediate facts in memory and to recall them from memory, rather than reproduce them over and over again. And sometimes that can have tragic consequences, or almost tragic consequences. There was a time in the space shuttle program where they had inefficient algorithms for controlling the directions of the nozzles on the rockets. They were millisecond off, which might be dangerous. They had to reprogram in order to make the program run more efficiently. One of the key processes for making programs run efficiently is the proper use of memory. Memory is something that you possess. You possess a working hippocampus. I'm going to make use of it. I want you to memorize certain facts. I want you to conceptualize certain definitions, certain words, certain processes. I want you to proceduralize. I want you to get those processes down. There is no higher level thinking or lower order thinking skills. There's none. There are just different brain regions, and I'm going to exercise all of them.